Hello, everyone. Welcome back. Today, I'm going to discuss the stability and the property anomaly of equilibrium systems. It is lecture 9. So before I start the new knowledge, new information, I'm going to have two additions. First is on slide 13, lecture 1, I presented the first law of thermodynamics. du equal to dq plus dw plus summation of ui dni. For this equation, we can get the definition of ui, which is the derivative of the internal energy to ni, and adiabatic condition, no heat exchange, no work exchange, and all other components are kept constant. So this is UI definition. And on slide 36, lecture 4, I presented the combined law. du equal to TdS plus dW plus summation of mu I dni minus d dx psi. That's for the internal processes. And I define the mu I as ui minus TSI, which equal to u to ni derivative, same derivative, however, under different constraints. So it's no work, the mass at the equilibrium, and also instead of dq to 0, it is S constant entropy. However, we know that S and Ni, they are related. So through this relation, we can see this equal to 0, this equal to 0, and most of all the Nj equal 0. Then we have this dq equal to minus TSI dni, which is not equal to 0. That means if we want to keep the entropy constant of the system, and if we add a mass into it, we have to remove some heat from the system in order to keep entropy constant. So this equals 0, and that equals 0. Okay, these are the two additions I would like to make for these two slides in lecture 1 and lecture 4. Okay, now we're talking about the stability of an equilibrium system. Again, we talk about entropy production inside the system. We remove a molar quantity from position 1 to position 2, which is represented by dx psi here. So we do Taylor expansion of the entropy production with T dips is entropy production. We talk about only one internal process. Of course, in reality, you may have many internal processes. So now do the first derivative, and the dx psi. Second derivative gives the dx psi square, and the third derivative gives dx psi cubic. So we represented we had this before. The first derivative gives the d dx psi. The second derivative, we put a minus sign in front of it. So the minus d2. So minus d2 equal to t over 2, and the second derivative. Then we have the third derivative, d3 here. At equilibrium, d equal to 0, or d dx psi equal to 0, more precisely. So at equilibrium, d equal to 0, and so d2 becomes important to determine whether entropy production is positive or negative. Okay, because d2, but d3 is less important, less significant unless d2 is equal to 0. That we can discuss in this lecture too. So we take the first, only the second term. So dips equal to minus d2 dx psi squared. Okay, so dx psi squared is always positive. Of course, dx psi itself is positive because we talk about the process moving forward. So the sign of the dips, the entropy production, depends on the sign of d2. So we know that for a system to be at equilibrium or stable, then this perturbation should not produce entropy. So entropy production less than 0, that means this is stable. Okay, that means d2 is positive. d2 is equal to negative derivative of the entropy production. So we can write this in the, but this stability in terms of combined law. Remember, du equals to minus c dips. So it's minus d psi plus d2 psi squared. So it becomes d2 psi squared. So d2 is positive. That means system stable when d is equals 0. So d2 is the second derivative of the u to psi squared, to psi. That means when system is at equilibrium with this and constant SV and Ni, and the internal energy at the minimum. So that's we call the minimization of the internal energy at equilibrium. Now we talk about the internal process that could be, we talk about the move the different molar quantity. If we move entropy from region 1, position 1 to position 2, then when we calculate D2, we equal to second derivative of U to S. That is the first derivative, U to S, and then another derivative. The first derivative of U to S equal to T. So T to S derivative must be positive. That means S increases and T must increase if the system is stable. Now, if we move volume, same thing, we got the volume U to V derivative, remember is minus P. Okay, so the minus P derivative to V is positive. That means if V increases, right, so you want to make it positive, so this P must decrease. Okay, because minus P should be positive change. So that means volume expansion and the pressure must decrease. Now, if we move the mass, just move one of the mass, Ni, component I, then we do the derivative. Again, now U to Ni derivative is equal to mu I. Remember, as mu I, as I mentioned before, to add that addition, is the mu I is on the constant S, V, and J. Okay, in that process, we actually have to remove some heat from that process to keep it a constant entropy. So for these three internal processes, we find that T to S go the same direction, minus PV go the same direction, and mu I and Ni change in the same direction. So we talked about it before, they are conjugate variables. It's Y and X, right, in our combined law, as we just showed in the previous slide, or last before. So that means for a system at equilibrium, the conjugate variables must change in the same direction, both decrease or increase at the same time. And we instead of the superscript, we use a subscript here to represent those quantities are internal variables, not exchange between the system and its surroundings. So now we remember that in the combined law, we can use internal energy, we can use another different energies, right? Okay. So now we want to talk about the when things are unstable. Okay. Unstable means that entropy production is positive. Okay. That means D2 is negative. That means internal energy, second derivative of internal energy to the internal process is negative. So we talk about it, if we have a diagram here, this is energy, or could be free energy too, and this is the psi, the state. You can see that, and in this region, the second derivative is positive. In this region, second derivative is positive, so it's stable. Of course, now you have metastable and stable because this has higher energy, could be reduced further by internal process. And then you have the region here. In this region of the states, you see that the system is unstable because the second derivative is negative. And between the positive and negative, of course, you have 1 equal to 0. Okay, that one we call the limit of stability, D2 equal to 0. D2 is it's between the conjugate variables, conjugate potentials, and the molar quantity equal to 0. So if we approach from the stable region, right? The stable region, remember it's positive, right? This is positive, and then it becomes smaller and smaller, then reach 0. Okay. Now, if we inverse this derivative, you go to xa to ya, then you find it becomes infinite, right? Because 1 over 0 is infinite, but 0 is positive 0. So this inversion gives a positive infinite. So we call this a anomaly because the divergence, right? The xa, the model quantity diverges at that point. So in this diagram, we also see that they are metastable. So this is stable, but energy is higher. So the system could change its state, go from here to there to lower its energy. Okay. So you have a driving force to change for the internal system to change from one state to another state to lower the energy. So we have now 3 stable states of a system. Could be stable, well, could be metastable or full stable in this range, and it could be unstable. Now we have 3 equilibrium here now. We have this is the equilibrium because first derivative equals 0. First derivative equals 0. This first derivative equals 0 too. So it's 2 are stable. This is unstable. And this is the metastable compared to that state. So now if you imagine that if all these points come together, okay, by changing the external condition, right? By, for example, change temperature. That's what we usually do. Change temperature and pressure. Then you could find a place where all these points come together, right? You have all this first derivative, second derivative, and third derivative. Okay. Typically, however, when the system changes a change condition, the system is stable, and if you change the temperature or pressure, this state may become less stable. Okay. And then become equilibrium because they have same energy. And then you become metastable like this, and then become unstable when change from one state to another state. So we can represent this process by this derivative I've showed before, Taylor expansion. So, however, there could be a point in the space in the variables, all of them equal to 0, right? Well, that means that we don't have the metastable range anymore. Okay, that means metastable, stable, and unstable all merge into one point. So system changes directly from a stable system, a stable state to an unstable state, without becoming metastable. So that point we call the critical point. At that critical point, for this one internal process, basically one internal variable, the first derivative, second derivative, and the third derivative all equal to 0. Of course, we also have that divergence. That's the xa to ya derivative equal to infinite. Remember, at stable, it's 0, right? It's positive larger than 0. So when you push 0 from positive to 0, inverse it gives the divergence of the model quantity xa. Okay, so we discussed all the stability in terms of the internal energy, which has S, V, Ni as its natural variable. Now, remember we talked about free energies. Okay, so this is what we had for the internal energy. We find that the conjugated variables will go in the same direction. The derivative is positive, which we do the ensemble is constant S, V, and Ni. Now, if we change to the enthalpy, H, now we remember that H has S, P, and Ni as its natural variable. Of course, we still have this condition. But however, this derivative is at fixed P instead of fixed V. We also had a Helmholtz energy. This time, we have the T is constant. Remember T is potential, it's not a molar quantity, okay? So that means other quantities, for example, V to P derivative or minus P, and the chemical potential to Ni derivative, okay, it's all positive, okay? But it's on the constant T. Of course, we also have our favorite Gibbs energy. Now it has both temperature and pressure are constant. That's both two potentials are constant. And now you simply this one can write a chemical potential of a component mu I to Ni in all of them, but this is fixed S and V. this fixed S and P, this fixed T and V, this fixed T and P. So same derivative. One question is that which one is larger or small? Is it larger or smaller? Okay. And turned out there are some rules on that. So the derivative, when it's derived from the fixed molar quantity or fixed potentials, they are different. Okay. And we know that the conclusion, let's start with the conclusion. The conclusion is that if you fix potentials compared to fixed molar quantity, this derivative and the fixed molar quantity is larger than the fixed when the derivative and the fixed potentials. So we can derive this one, we can prove this one, a little bit more math here. So if you have difficult to follow it, please go back to learn a little bit more about the Jacobian. Okay, Jacobian describes the relation between two functions, YB and YC. That are two potentials we have in our case as function of XB, XC, and XB, XC, because both of them are the function of XB and XC. We talk about have two molar quantities in the system and two potentials. We define the Jacobian matrix as a derivative of the two functions to two variables. So it's YB to XB, YB to XC, two variables, two derivatives. Then you have the YC to XB and the YC to XC. So we can solve this matrix. We got a determinant. We got the this one times that one. Okay, so YBXB, YCXC minus YBXC times YCXB. Okay, this is called Jacobian. So it's all under constant XB and OXC. Okay, when you take derivative to XB, X is constant. So it's all molar quantities are kept constant in our case here. So the relation is that derivative of YB derivative of YC is equal to the Jacobian matrix times DXB and DXC. Okay. So we want to prove this relation, so we need to solve this one and compare that one. Okay. So now we say we can do the DYB, right? To derivative of XB, we move XB on that side, and the constant YC, that will be equal to J times XB. So we basically move YC on the other side. So it's YC to XC, right? Divided and XB. So this is YC, and this is YC is constant, capital constant. This XB is capital constant. Then we know that Jacobian matrix has this. It's represented by this equation. So we take this one here. We'll put it in here. So this one divided by YCXC. So it cancels the YCXC first one. Okay. So it's the remaining is YB to XB. And then this will be YBXC, YCXB still divided by YCXC. These derivatives are taking either a constant XB or constant XC. We can see that this is less than YBXB and constant with XC kept constant. Okay. So this is YBXB, right, with the XC constant. So this one equal to that one. Okay. Now let's look at the second term here. So we know this is positive, right? For stable system is conjugate variable, they're positive. And this YBXC and YCXB, we don't know it's positive or negative because they're not conjugate variables. Actually, they can be both positive or negative. Okay. However, they are equal based on the Maxwell relation. Remember that we talked about the Maxwell relation before. You switch variable YB to XC or YC to XB. It's basically the second derivative of the free energy, of the internal energy. So they are equal. Doesn't matter. If both are positive, they are both positive. If one is positive, another is positive. If one is negative, another is negative. So time together is always positive. So the positive divided by positive is positive. So a positive value minus a positive value is less than itself. Okay. So now we prove. Now it is proved that it's a derivative between the conjugate variables with the molar quantity fixed is larger than the one with one of the potentials fixed, one or more potential fixed. Okay. Okay. Of course, we know that we just in last lecture we talked about the Gibbs-Duhem equation. if all the other potentials are fixed, this potential is fixed too, right? Because all the potentials are related. Okay, that's the limit we can reach. So that means you fix all the potentials, now the derivative is also equal to 0. Okay, so it's not changeable. So that's because the Gibbs-Duhem equation for a homogeneous system. Okay, that's the lecture 9. Thank you very much. And I'm looking forward to hearing your comments, and see you in the next lecture. Bye.